Lesson 2.2 covers functions and function notation. So the definition of a function, how do you check to see if a graph or a table or a situation or an equation is a function? Those are the things we'll cover. So the definition of a function here to start off with, mathematically, a set A to a set B in a relation that assigns to each element x in the set A exactly one element y in the set B. So the main thing here is each x gets exactly one y. That's the main point there. The set A is the domain. The x values are the domain, and we'll talk about that more. And then the set of B values, which is the y, or the set B, which is the y values, is the range, also called the output. So here, if we do some highlighting, the domain, which is the input, are the x values, and the range, which is the output, are the y values. Characteristics of a function. Each element in A must be matched with an element in B. So each element from the first set must go to something in the second set. Some elements in B may not be matched. That is okay. So when it talks about sets A and B, think about set A as your x values and set y as your b values. It's the x values that really are important here. That's what we focus in on. So when we put an x value in, what number one is saying is each x value has to have a y value in that set. But it's okay, and we'll look at a picture, it's okay if some of the y values aren't like taken by an x value. That is okay. We'll look at a picture to clarify that some more. And it says two or more elements in A may be matched with the same element in B. That is okay. Two different x values can go to the same y value. That is fine. And then the last one, before we look at some pictures, the element in A, which is the domain, cannot be matched with two different elements in B. So let's go to some pictures to look at that. But first, a couple more examples here to look at. So to determine whether a relation is a function, you must decide whether each input value is matched with exactly one output value. That's the main idea right there. That's what we need to know. Each input can only have one output. Nothing else matters. The outputs don't necessarily matter. Okay? Focus in does on each input only have one output. And then when any input value is matched with two or more output values, it's not a function. So here's a picture from what we were just talking about, kind of put everything together. So here we have a function that relates the time of day to the temperature. So our time of day, that's our x value. And then the temperature over here is representing the y value. So the input is the time, the output is what's the temperature at that time. So notice how, if we zoom in on these are the x values, each x value has one line coming out of it. It doesn't matter where that line goes. As long as there is only one line coming out of each one of those, it is a function. Okay. Off to the side here, they describe this as set A, which are the x values. It's also known as the domain, and it's also known as the input. So there's four different ways to describe that one set. It's set A, it's set of x values, it's the domain, and it's the inputs. Now, if we go over here to the outputs, to the y values, remember these aren't as important. Okay? So if you look, the 9's got one value coming into it here. That's fine. The 13's got one. The 15 has two. That does not matter, right? The 2 into the y's does not matter. It's only, remember, how many arrows are coming out of the x. X is our focus here. So it's okay if the 15 in the y has 2, and it's okay if there's all these elements over here that don't have any. Okay, that's fine. Okay. Remember what the focus is, again, over here with x, every element in x must have one element in y, so one value coming out of each one. No doubles, and if I had an extra one, like if I had a 7 over here that wasn't taken, then that wouldn't be a function because that 7 has nowhere to go. But we don't have a 7. So everything is good here. And then again, the terminology, that b value, the b set are the y values, the range, the outputs, and then you can list them all. All right, these can also be written as ordered pairs. So these ordered pairs here represent where 1 goes to 9 is 1, 9, where 2 goes to 13 is 2 and 13, and so on. 4 goes to 15, it's over there. 3 goes to 15, that is okay. 5 goes to 12, and 6 goes to 10. Okay. So when you're looking at ordered pairs, I actually think this is the easiest way to tell if you have a function or not, because with ordered pairs, you just have to look and see, are there any x values that repeat? So I have 1, 2, 3, 4, 5, and 6. So no x values repeat, which means it is a function. It does not matter if the y values repeat. These 15s here don't matter. That's fine. It's only the x values we're focused on. And then there's 4 ways to represent a function, and we'll look at an example of each of these. Verbally, so that would be a sentence describing a situation. Numerically could be a table or a list of ordered pairs like we have above. Graphically would be a graph. For that, we use the vertical line test. And then algebraically is an equation. So we'll look at one of each of those, or a couple examples of each, on the next slide here. All right, so number 1, determine whether the relationship represents y as a function of x, which just means, is it a function? So letter A is an example of a verbal description, telling us what the input and the output are. So the input value is the number of representatives from a state, and the output value is the number of senators from that state. So what I like to do here is I like to kind of draw and visualize. So I would say, well, okay, my x values, they are state representatives. And then if I kind of make a table here, my y values are the state senators. Now, if you're not familiar with this, you might need to do some background searching. It's as easy as opening up Safari and Googling, how many representatives does a state have? How many senators does a state have? So if you're not familiar with a situation, that's okay. Be a problem solver. Google it. That's what I do. So it is totally fine to use your resources if you're not familiar with the situation. So if you look that up, if you're not familiar, what you'll find out is each state has a different number of representatives based on their population. So this number can change. Okay. However, the number of senators is what's constant. Every state has 2 senators, no matter what. That's the side of the house that is equivalent for everyone. So we've got all these numbers over here for our x values, right? But we've only got one number for our y value. So for example, let's say this is Minnesota. Minnesota, no matter how many state reps they have 2 senators. Illinois has 2 senators. Michigan has 2 senators. Iowa has 2 senators. North Dakota has 2 senators. Okay, so none of these numbers, each number here, no matter what the numbers are, each number here is only going to go to one output. It can only go to 2 senators. And because there's only one option, there's only one output for each one, this is a function. This is yes. For that verbal description. However, if it went backwards, if you flip-flopped these two, and I made x my column that was only 2, and y my column that was all these numbers, that would not be a function because my 2 would be going to all of these different values. So my x value now would have a whole bunch of outputs, and that is not a function. So it does matter the order and what is x and what is y, because if I were to switch the order for this number 1, it would not be a function. All right, number 2, numerically, when you have the numbers written out, it's really pretty simple. You focus on the inputs. Are there any repeats? Do any inputs have more than one output? And the answer here is yes. My input of 2 goes to 11 and it goes to 10. That cannot happen. So this is not a function because x equals 2 has 2 outputs. So really, if any of these repeat, these cannot repeat. If they don't repeat, you're good to go. If they do, it's not a function. Graphically, we can use the vertical line test. You have used this before. And that is where you draw a vertical line. In this case, there's just five points. So if you draw a line through each point vertically, so straight up and down, only 1 point should be on each line. Each line should only cross that function one time. And in this case, they do. If I were to connect these, it would make a parabola, and each red line would only cross that parabola in one spot. So yes, this one is good to go. If I took this parabola and I flipped it around, so if I said it's going to do this instead, that would not be a function, because if I draw a line, I'm going to cross twice, and that cannot happen. So this one is not a function. All right, now equations. The easiest way to tell with an equation is solve for y first, and then figure out how many, if you have one input, how many outputs could it have? So here, if we solve for y, we'd subtract x squared. We get y equals negative x squared plus 1. So now if we look here, if we pick an x value, let's say x equals 2, and we substitute a 2 in, how many answers are we going to get? Well, we'd get negative 4 plus 1, which is negative 3. We get one answer. So there's one output. Okay. There's no x value that I could substitute in here and get more than one answer from it. Okay. So because this has one output, yes, this is a function. Now let's look at number 2, or the second one here. Solve for y, so subtract x squared. And we can write that as 8 minus x squared, whichever order doesn't matter, and then we do the square root. So we get y equals plus or minus, and then just leave that the square root of 8 minus x squared. Now right away here, if you have to take the square root and you get this plus or minus is telling me there's two outputs. Right? One positive, one negative. So this is not a function. So right away, I don't even have to try any numbers here. If I have a positive and negative, right away it's a no, because that's two answers. The third one is solve for y, and we have a square root. Now, when we have a value under a square root, in order to get a real answer, it cannot be less than 0. Okay. However, if I substitute in a number, how many answers am I going to get? So like if I do x equals 5, I get the square root of 5 plus 5, which is a square root of 10. Now, keep in mind, I do not have a plus or minus here. I did not have to take the square root. So even though there's a square root given, okay, this equation is telling me that's what y is. Y is only the positive square root. There's no negative here. So because this is already solved for y, do not add a plus or minus in if you're not taking the square root of both sides. So this is only the square root of 10, and that's one answer. So this is a function. So just because this is a square root, there's no plus or minus here because we did not have to take the square root to solve it. It was already given to us as only positive. And then function notation. This is one you've seen before. So the benefit of using function notation, which is f of x instead of y. So y is the same thing as f of x. Okay. It tells us what the input and the output are in the final answer. For example, if we look at number 2 here and we do letter A, I want to find h of negative 6. Well, that means I take my function and I substitute negative 6 in for my variable, which in this case is t. So I would say h of negative 6 equals 3 times negative 6 squared plus 9. Order of operations, exponents first. So I'd get 3 times negative 6 squared is 36 plus 9. And then just keep on simplifying here. So I would get 108 plus 9, which is 117. So my final answer would be h of negative 6 equals 117. And the reason these are helpful is because this tells me the input was negative 6, and then the answer or the output was 117. So if we just said like y equals 117, I don't know what my input was. But if we use this function notation, it tells us what the input is. All right, letter B. Now my input is t plus 3. So that means this entire thing, I'm going to rewrite my function. This entire thing is going to go wherever the variable. So where this t is, I'm going to substitute in this binomial t plus 3. Here's what that looks like. So I'd have equals 3, and then I'm going to substitute in t plus 3, that is squared, and then plus 9. Okay, from here, we need to, again, exponents first. So we'd have 3 still, and then we need to do t plus 3 times t plus 3. And then we just need to finish simplifying. So multiply, keep that 3, do your FOIL. So t squared plus 3t plus 3t plus 9, and then plus 9. And then you can combine like terms, or you can distribute the 3 next, doesn't matter. So if we distribute the 3, and remember, all we're doing is simplifying this down as much as we can, combining like terms, multiplying as much as we can. So in this case, I can combine my constants at the end to get 3t squared plus 18t plus 36, and this is my h of t plus 3. So it's telling me if I substitute in input t plus 3, and then the output is this trinomial, which is fine. It's simplified as much as we can. 3t squared plus 18t plus 36. Our last example is having us subtract two things. So I'm going to rewrite our function just right above here so we have it to look at. Okay. So what the first piece is asking me for is just the original function. It's just h of t. So for this, it's just 3t squared plus 9. It's the exact same thing. And then I'm subtracting. And when I subtract, I want to put whatever I'm subtracting in parentheses. And in that, I'm going to substitute a 5 in for the t. So we get 3 times 5 squared plus 9. And then we can simplify. So working inside the parentheses, I'm going to do my 5 squared first. And then if we simplify in the parentheses, we get 75 plus 9. And then we can go ahead and combine those. So we get 3t squared plus 9 minus, and that'll give us 84. And then we can go ahead and subtract that 84, so 9 minus 84. So we get 3t squared minus, and then that'll give us 75. So there you have an example of all the different representations of a function.